now I'm going to actually introduce one of our show's producers here, okay? Remember, as you saw, that was a production of Montana State University, and Professor Nicolás Yunes was one of the co-founders of the Extreme Gravity Institute there, and he had worked together with various organizations, including the Montana State University School of Music, as well as, I can read all of these off the top of my head here. I believe he got funding also from the Montana Space Grant Consortium, the American Physical Society, and various offices of the administration there as well. Anyways, Professor Yunes, he got a bachelor's degree over at the Washington University in St. Louis. He got his PhD over at the at the Pennsylvania State University. He did some postdoctoral research over at Princeton as well as at MIT and Harvard. So I'd say that was pretty good there. About 3 years ago, he joined the University of Illinois' faculty and is a founding director of the Illinois Center for the Advanced Studies of the Universe. So we welcome Professor Yunes, Nico, to join us here today. And I'd say that as he comes up here to start this Q&A session, let's give him a round of applause for the show, please. Right. So what we're going to do for this Q&A session, folks, I will carry around the microphone so that everybody can hear exactly what you might be asking about the show. Feel free to ask him about the production. Feel free to ask him about the science. We'd love to hear what you have to say in terms of feedback. Remember, this is the first time this has been shown at our planetarium, okay? Before we get to any of those questions, Nico, did you have any remarks you wanted to give to the audience at the onset?
Thank you. Thank you for the introduction.
You're very welcome.
And thank you very much, Eric, and the rest of the staff here for putting the show up. I really want to open the door for questions. I thought it would be better, instead of me just giving another 30-40-minute lecture, since you've already been sitting there for a little while, we would just have a little conversation and see where that takes us. I can tell you about how the show was made. I can tell you about the science. I can tell you about lots of things. So what do you want to chat about? Yes?
I have a question.
Question.
Thanks for your patience. I'll come back to you. Just put this below your chin, okay?
Yeah, not a problem.
Thank you so much.
So my question to you would be, if a black hole is a singularity point within the universe that has basically immense gravity that nothing can escape from, things like that as well too. And if the Big Bang Theory was correct that at the start of the universe there was a singularity, what is the thought or theory behind the actual force that was able to counteract the gravity, pulling it into that singularity to then create that massive explosion, which we now call the Big Bang?
Great question, highly technical. Here, I can take this and pass it around on this side.
That's great.
So when we talk about singularities in physics, we don't necessarily mean a point with infinite pressure and infinite gravity. What we really mean is a point that, where physics breaks down, our current understanding of physics breaks down, and we don't really know how to describe that point. There are ways to try to extend Einstein's theory of general relativity and get it to play nice with quantum mechanics, and those extensions attempt to resolve this singularity. And what they say is that no, pressure, density, gravity, all these things don't become infinite at the center of a black hole, but rather they are very large, but that curvature is curved away in some sense, so it doesn't become infinite due to quantum effects. Precisely how that happens, nobody really understands yet. There are attempts to explain it, but it's science, and it's very hard to verify these predictions because black holes are real far, and if you were to go there to try to check if your theory is right, then there would be no way for you to tell anybody else outside of the black hole. So the same thing happens at the Big Bang. The Big Bang is a point that is singular, infinite in our evolution of the cosmological equations of general relativity, which are called the Friedmann equations, because of this guy Friedmann that was one of the first people to derive them. It doesn't necessarily mean that this point had infinite pressure and infinite density, therefore was a black hole. In fact, the singularity of a Big Bang is a different type of singularity from the singularity of a black hole. We call one a space-like singularity and another one a time-like, because he has very specific mathematical meaning, but they're not quite the same. So the Big Bang didn't start as a black hole that then exploded. But it's sometimes confusing because we use the same word and we just shorthand it to singularity, and then people sometimes get confused. But that's a great question. Very technical, but we can go with less technical. Yes.
I've been reading about quark stars.
Quark stars.
So how much more massive is a quark star compared to a neutron star, but less than enough mass to make it a black hole?
Great question. So yes, people have been thinking about objects called quark stars. So you see, we talked about neutron stars and we talked about black holes in this show. And so what are these things? So if you take the sun and you compress it to a ball of a diameter of roughly 20 kilometers. So in your units, that would be 14 miles, more or less. Then, and what is that? Is that the size of Champaign plus Urbana, maybe? So if you make the sun fit inside of a ball the size of our town, then you would have a neutron star. Matter would be so compressed that neutrons and whatever protons they would be touching each other essentially, and then forming this soup of quarks that are inside these protons and neutrons. And so a question right now in nuclear physics is precisely what happens at the centers of these neutron stars. Could there be a soup of quarks and gluons and other things inside? That's called a core or a quark core, if you want. And pushing nuclear physics a little bit further, you can imagine that there could be a star that's essentially just made out of quarks alone. And these are very hypothetical stars, and they are stars that essentially don't have a crust. It's just the core alone, if you want, a little bit puffier than it would have been for a neutron, for the core of a neutron star. So these objects, instead of having something like a radius of 11 kilometers, they would have a radius about 7 or 8 kilometers. So it would be a bit smaller, and they would still shine in some sense because they interact electromagnetically, and they would still have the mass roughly of a neutron star, so roughly the mass of the sun, maybe a little bit lower than that. Of course, if I compress the star even further, then I make a black hole, right? But I have to compress it significantly further for that star to become a black hole. You would have to have a radius of about 3 kilometers or so. So what we're now trying to figure out is whether these quark stars exist, because nobody has really observed one. At least there's no evidence for a quark star. And we're also further trying to figure out whether the neutron stars that we observe, whether they have a quark gluon plasma core inside of them. So we're trying to see what observational signatures we can extract about the interior of neutron stars. And some people here in the audience, like right over there, are nuclear physicists, and they work at the University of Illinois here to precisely answer that question, among many other things. Follow-up question.
So it wouldn't have to be more massive than a neutron star?
That's correct. It wouldn't be more massive. If it were more massive, the gravitational field, the gravity would sound so strong on that object that it would collapse. We call it, if you keep on increasing the mass, the radius, the gravity becomes stronger, right? So the radius becomes smaller. The object becomes more compact, we say. And at some point, the mass becomes large enough that all of the pressure generated by quantum mechanical effects and electromagnetism and other things cannot, fight against gravity, and gravity wins, because gravity always wins, and it makes a black hole. Does that make sense? Sammy. Excellent. It's going to be a very technical question.
How do you know gravitational waves exist?
Great question. How do I know that gravitational waves exist? So as we saw in the show, gravitational waves are these like vibrations and undulations of space and time, of gravity itself. And they propagate in every direction from a source when the source does something violent, like explode or collide with something else that's very massive. And so those waves travel in opposite directions, and they go through matter, like us, all the time. They're like gravitational waves going through you, like right now, but the effect on you is so weak that you don't feel any tingling or anything like that. but there's tons of gravitational waves going through you right now. So what we need to do to see if they're real is we need to detect them. We need to build a super fancy experiment that's huge and super sensitive so that you can feel these tiny vibrations in gravity. So that's what happened. In 1970, a guy called Ray Weiss gave a homework problem to his grad students. How would you go and check that gravitational waves are real? You know, roughly that was a homework problem. And he asked them to build, or to not build, of course, that would be too hard for a homework problem, but like design, at least on a piece of paper, how would you build an instrument that could detect gravitational waves? And the students went and like tried to do something, and they all got it wrong. And then Ray tried to like figure out what the answer was, and he realized, oh, maybe the problem was a little bit too hard because I don't quite know what the answer is. And so, but eventually, about 6 months later, he figured it out, and he published it in an internal MIT document. He was an assistant professor at MIT at the time. That design is what, 50 years later became the Laser Interferometer Gravitational Wave Observatory, LIGO, which we have one in Washington State in the Nuclear Reservation in Hanford. I don't know if you know that area. Tri-Cities have beautiful cherries. I used to go and pick up some cherries for my family when I was younger, and I was forced to, be at the instrument. And then there's another instrument in Louisiana in Baton Rouge, effectively. And so what these instruments are is giant tubes, giant tubes in the shape of an L. Okay, and these tubes are evacuated. They don't have any air inside. One of the most perfect vacua in nature, well, not nature, that are human-made on Earth, is inside of these tubes. And inside of the tubes, they shine lasers. And so what they do is they have this L shape, trying to prevent the microphone from falling inside of the, there we go. So they have this L shape, right? And they shine a laser from here, and so part of the laser goes that way, part of the laser goes that way, and they have mirrors at the end. And the laser bounces back, comes back, and recombines. Okay? And so what gravitational waves do, Sammy, is they change the way that those light rays, those laser beams recombine. And by checking exactly how they recombine, we can tell that a gravitational wave is going through. And so that's how you know. And then, after you detect them, you go and you pick up the Nobel Prize in Stockholm, and everybody's very happy. Yes.
My question.
No mean questions to Daddy.
My question is, if a black hole exploded, would everything inside it get free?
Great question, Penelope. So black holes, they essentially eat everything that's around them. Everything that's close to a black hole gets to get swallowed by that black hole. And the gravity is so strong that nothing can really escape a black hole. So black holes cannot really explode. But turns out that because quantum mechanics, which is part of physics where like really funky things happen, do play a role for black holes. And there was this guy in 1960 called Stephen Hawking that started thinking about how quantum mechanics and gravity could play well together. And he discovered that black holes actually are not these perfect vacuum cleaners, but rather they emit a form of radiation, a form of light. So it's like they're exploding, but very, very, very slowly at very, very, very low temperatures. And so a big question to this day is what happens after all of that radiation leaves the black hole and there's nothing left in the black hole? What happens then? Does the black hole that used to be there sort of evaporate because it exploded, like you said? Or is there something left after that explosion? That is called the information loss paradox, and whoever resolves that will become very, very famous. Good question. Yes. Who had their hands? Yes.
When there is a gravitational wave and another gravitational wave meets it, what happens and why?
Great question. So gravitational waves are being produced constantly, right? Like I said a second ago. And there are so many gravitational waves that when they come together, they can interfere and they can produce this sort of very choppy background of gravitational waves that permeates the cosmos. Okay? That's called the stochastic background of gravitational waves. And of course, every now and then, something goes boom sufficiently close to us that it rises above that background, and that's what we call like, oh, the gravitational waves. I can sonify and I can show you pretty pictures, and then I can detect, and then I can learn something about the thing that made the wave. But behind those large waves, there's this background, okay? Because of interference. It's very much like the ocean. Okay, when you go to the ocean, you see like there's this choppy ocean, but sometimes with a cadence, when you go up to the lake, you see these waves hit the shore. And every now and then there's a tsunami, and there's a big wave, right? So there's a very large group of people right now spread around the world that are trying to detect that stochastic background. But the problem is that background is, well, it's very low amplitude, it's very hard to detect. And it's easiest to detect in some sense at very, very, very low frequencies. At frequencies so low that if we try to observe those waves with these LIGO instruments, we wouldn't be able to. Because it turns out LIGO is mounted on the surface of the Earth, and the surface of the Earth shakes constantly. So LIGO is an amazing seismometer. And that means that it cannot resolve frequencies below the natural frequencies of vibration of the Earth's crust. So what very, very smart astronomers figure out is that instead of using light that is shot out to a tube and then out to a tube over there, instead they were going to use the light from neutron stars themselves, because astronomers have detected tons of neutron stars in the Milky Way. And some of them are amazing clocks. They have this very strong light that is sort of funneled into a cone, and those cones sort of sweep past Earth with a very sort of stable period. And by counting the ticks, you can sort of kick time. And so if you have a pulsar, like over there, you can detect the bits from that clock, but maybe you have another pulsar over there. And so you can detect the bits from that clock. And maybe you have another pulsar over there, and you can detect the bits from that clock. Each of those arm lengths, or each of those lines of sight, forms like an arm length for a gravitational wave detector. And by combining them all, they can try to detect this stochastic background. That effort is called a pulsar timing array. And it requires a worldwide collaboration between scientists in the United States, in South America, in Australia, in Europe, and so on and so forth. And they are, don't tell anyone, cut the camera. I'm just kidding, you don't have to cut it. But they're very close to announcing the first discovery of this background. Like, very close.
So you're saying they're actually working together?
They're working together. Isn't that amazing? Even though the Australians don't always get along with the Europeans or the Americans, but yeah. And so Arecibo, like that giant dish that we have in Puerto Rico, where they filmed Contact and many other movies, James Bond and whatnot. So prior to the antenna breaking in half, that used to be used in part to observe pulsars and to track these pulses. And they have now collected enough data that in principle, they can detect this effect. Yes, another question. Go ahead.
So I know that Stephen Hawking predicted the possibility of primordial black holes. Do you suspect that those, when they finish decaying, would cause gravitational waves?
Good question. So let's talk about what a primordial black hole is. So I told you what a black hole is. A primordial black hole is just a black hole that was not made because a star exploded, went kaboom, and the core then collapsed into a black hole. Instead, a primordial black hole is a black hole that was formed in the very early universe when somebody asked me about the Big Bang, right? So more or less right after the Big Bang, everything was a big hot soup, and structure was slowly forming, and some of that structure, some of that gas, some of that material that was cooling and expanding might have formed a small black hole, okay? So those small black holes are called primordial because they come from like the early universe instead of from stars exploding. Now, those small black holes, unlike black holes formed by collapsing stars, they can have very tiny masses. So you see, if your stars are massive enough, like above 20 times the mass of our sun, when they go kaboom and collapse, they form a black hole that's typically above 5 times the mass of our sun. So they're big, beefy guys, or girls. And they can go all the way up to like billions of times the mass of our sun due to growth from collisions or growth from like accreting material or whatever. But typically it's not, we don't think it's easy to form astrophysically. Black holes are smaller than the mass of our sun. Primordial black holes, however, can have any mass they want, right? And because they're so small, it would be very hard for them to grow. Because a tiny bullet that's like running through the cosmos and like collecting gas as it goes through will suck in material much more slowly than something heavier with a bigger cross section. So then the question is, do these things exist? First of all. And the answer is, we have no idea. We have never detected a primordial black hole, not for lack of trying, but they are just not in the data, at least not right now. So one way to detect them would be by seeing the gravitational waves they emit when 2 of them collide. The LIGO instruments are sensitive to detect some primordial black holes of a certain mass if they're close enough. They have not yet been detected. Let me just end. Now, if they exist, then you can ask, well, will they Hawking evaporate? And the answer is yes, all black holes Hawking evaporate. And what's the end state of those primordial black holes after they've emitted all of this Hawking radiation? And the answer is we don't know. Just like we don't know what the end state is of a big black hole that is Hawking evaporating. But the thing is that it takes a very long time for this radiation to actually escape the black holes and like shrink it enough. Because, a black hole is typically, maybe a fraction of the mass of the sun if you are primordial, or a few times, or maybe tens of times, or maybe hundreds of times the mass of our sun. The mass of our sun is huge. It's like 10 to the 30 kilograms. So it's 10 with like 30 or 29 zeros after it. Hawking radiation is tiny. It's like, imagine like tiny particles, like photons, leaving with some energy from the black hole. So it would take a tremendous amount of time for that Hawking radiation to evaporate a black hole completely, even if it's primordial. How much time? Longer than the age of the universe. So we're safe. And unfortunately, we cannot really test them either, but yeah. Another question, yes.
As you were just saying, we are safe.
Yes.
With the knowledge that you have accrued about black holes and the infinite number of the universe, does this ever cause you to be more afraid?
Does this cause me to be more afraid? So first of all, I should say that thousands, tens of thousands, many tens of thousands of physicists have devoted their lives over the past 100 years to sort of understand these things. So it's by no means just me. And am I afraid of black holes? No. The probability of a black hole affecting us in any way is tiny. It's ridiculously tiny. It's way more likely we will be hit by 3 lightning things at the same time. Like, it's just not going to happen. It's much more likely that we will annihilate ourselves in other ways, which do keep me up at night. But it's not the black holes that worry me. Yes.
How long does it take disruptions in gravitational waves to reach us or for us to detect them?
Great question. So black holes are everywhere. Okay, so there's one black hole at the center of our galaxy called Sagittarius A star, of recent fame because another group of physicists and astronomers took a picture in this so-called Event Horizon Telescope. That is 8,000 parsecs away. And help me, Eric, how many light years?
26,000 light years.
I knew you knew that.
Sorry, I'm not on the mic, so I could yell.
26,000 light years. So that's 26. It would take 26,000 years for light to get from the center of our black hole, the black hole at the center of our galaxy, to us. The gravitational waves that we have observed are way farther than that. They're in other galaxies. And so the first event was detected at 400 megaparsecs. Okay, so that's 400 times 10 to the 6 parsecs. So 10 to the 8 parsecs. So that is, we're now talking about millions and billions of light years, depending on precisely which event you're talking about. So this collision had to happen, and gravitational waves travel at the speed of light. That's the other piece of information I should tell you. So if the gravitational waves travel at the speed of light, and they are a distance of, let's say, 1 million light years away, then that means that they take 1 million years to get to us. So this thing collided a long time ago, like, age of the dinosaurs. What is that? I am not an archaeologist or paleontologist. Paleontologist, thank you. But yeah, like way before humanity was a thing. But we're detecting them now, and so it's a bit of a coincidence that the instruments were online sort of at the right sensitivity to detect these things for the first time, and then boom, this thing was detected, or this thing went boom like the right number of millions of years before, so that we could just detect them right when the thing turned on. And it was a bit of a golden event. It was super loud. It was super, the wave was very clear. The amplitude was so large that it was nearly impossible to calculate how certain we were that this was a signal and not noise. Like, it's hard to calculate the number of nines after 99% that this is a true event. And then, of course, there's been about 90 other observations since then. So many of them not nearly as loud or nearly as certain as that one. And they're all more or less spread away between roughly a billion years away from us in light years. Yes.
Yes. So you were saying that we know that there are black holes that have existed since the universe existed. So how do you know how old a black hole is? Is it by the amount of radiation it has?
Great question. So how do we know how old a black hole is? So you said a second ago, as you were framing your questions, that we know that black holes have existed since the beginning of the universe. So let me just correct that. We don't know that is actually true. I mean, there's a hypothesis that these primordial black holes exist, but who knows? Until we actually detect one, we don't know for sure. However, it is true that we believe black holes formed, at least the first black holes, a long time ago. So long that we stopped using years to count, and we use something called redshift. So sometime near after the Big Bang, these first black holes formed. And then they began to grow, and they began to grow, and they began to grow. Since we don't know exactly the mass they had when they formed, because there's no way to necessarily observe those, we don't know how long it took for them to grow to the size that we see today. Moreover, we don't know exactly how they grow. So we think we know, but it's not like we have been watching the cosmos for millions and millions of years to actually track, and it's not like we have the technology to see black holes colliding in real time. These things take forever. So we don't know, for example, if black holes were formed already, like a certain heavy, or whether they grew due to collisions with other black holes, and then other collisions with other. Is this like a second generation black hole formed from the collision of two other black holes? Is it a third generation, fourth generation? We don't know. What we do know is that there's strong evidence for there being a pretty sizable black hole in the center of most galaxies. We also know that galaxies collide, and we also know that the black holes at the center of these galaxies also collide. And we have some evidence, some with telescope evidence of these things happening. Now, because of LIGO, we also have evidence that much smaller black holes collide, black holes of the size of tens of times this mass of our sun. But it's not, there's no way to tell how, whether they're teenager black holes or they're like elderly black holes. I mean, if you had to ask me, the smaller ones are probably youngsters, and the older ones are more elderly, but it's no way to tell you exactly.
To tangent off of that question, would we be able to use the new James Webb Space Telescope because it is specialized in infrared sight compared to Hubble, which is visual light, to actually look back into the early universe, which I know is one of the things that they're looking to do with that, to actually see if there is a formation of a black hole in the early universe, while they're also looking to see the formation of galaxies in the early universe, if we think or theorize that there is a black hole in the center of every galaxy.
Right, great question. So let's talk about the Webb. The James Webb Telescope, also known as JWST, was launched not that long ago, and it was in the news, and you saw the thing launch, and you saw everyone hold their breath because it cost a fortune, and then you saw the thing like separate, and then everybody held their breath again because like maybe it explodes when it separates. And then it had to like get to a certain point in our solar system so that it could be sort of stable in a stable orbit. And that was the third time when we were all like, is it going to, get there and stay there? And it did all those things. The engineering actually worked, and the scientists, and it was mostly NASA, made this happen. And now, the James Webb, finally has the first images of these galaxies and stars that it's observing. It's like way more powerful than Hubble. That was what we were using before. And so because of how sensitive it is able to see light emitted by galaxies that are really, really far away, much further away than we had seen before. To see black holes, though, that's a different story. Okay? Because black holes, relative to a galaxy, are tiny. Okay? I'm talking about like, 10, black holes are a mass of 10 to the 6 times the mass of our sun, or things like that. They seem like huge numbers. Black hole with 1,000,000 times the mass of our sun. But because they're black holes, they're really, really compact. So even 1,000,000 times the mass of our sun fits in a fairly small volume, about a radius of 1,000,000 kilometers. And a radius of 1,000,000 kilometers in astrophysical scales is nothing. It's a point. Okay? And so if you want to see a point in this haystack of other nonsense, then you need to have something that point is emitting at sufficiently high luminosity for you to be able to say, aha, there's a black hole. And typically what we use are X-rays for that, which James Webb does not. Gotcha. So we'll try that. Yes, we're here. Feel free to ask me about questions that are not about physics, it's okay.
Well, I just wanted to give a plug to the NASA website, because they have managed to capture the atmospheric overpressure waves of gas falling in, boosted the frequency to human hearing range, and you can actually hear the sound of matter falling into a black hole.
Yeah, pretty cool.
So you've heard that?
Yes, I have heard about that. That was brought to my attention. I do not follow every single thing that NASA does because it's just too much. But there's this thing called Black Hole Week that we all celebrate once a year. And it was last week? No. Last month? I don't know. In May. Okay, it was in May. And during Black Hole Week, they announced this thing of the sonification of pressure waves from a galaxy cluster called Perseus. Okay, so for everyone else, this is what happened. There's a galaxy cluster. What's a galaxy cluster? It's a bunch of galaxies that are close to each other. That's galaxy cluster. Okay, and in this galaxy cluster, there's like a really big black hole. Okay, and this galaxy cluster, unlike most other parts of space, which are sort of in vacuum, this cluster has a lot of dust and a lot of gas. And so through various surveys, people were able to extract information about pressure waves in this gas that are associated to the black hole. So what they then did is they took these pressure waves and they played them through speakers. Unfortunately, that's about 57 octaves lower than what we can hear. So they didn't hear anything. So then they said, aha, we're going to fake it and increase the frequency 57 times, it's 57 octaves, so that we can hear these sounds. And they did that, and then they played this in a very recent, this is called a sonification. They take data and they turn it into sound. And then they publish it in the NASA website, and it's pretty amazing. When you like hear it, it's like, whoa, that's pretty cool. I like my soundtrack better, personally, but that was pretty cool too. Well, 2 questions. I saw Alexandra's hand first. So.
What happens to something when it goes inside of a black hole?
What happens to something when it goes inside of a black hole? That's a great question. That's a question that I sometimes ask my grad students when they are taking a test, right? So imagine that you are at the very edge of a black hole. Inside of this of this edge, nothing can escape. But outside, if you have a rocket ship that's strong enough, or like a jetpack that's strong enough, then maybe you can escape. Now imagine that you get to the very edge of the black hole and you stick your hand in. Then what happens? What happens is that you fall into the black hole because now your hand cannot escape anymore. And now you're beginning to fall in. Let's say that you're falling into a black hole that's huge, like the black hole at the center of our galaxy. Then what happens? You begin to fall into the center of the black hole. And gravity begins to get stronger and stronger and stronger. And let's say, just for kicks, that you're falling head in. Because why not? Maybe you want to see which way you're going, right? So you're falling head in, and gravity is so strong that the forces of gravity on your head, which pull you toward the center of the black hole, are stronger than the forces of gravity on your feet, which are also pulling you toward the center of the black hole. That differential acceleration, that thing causes a stretching of your body and turns you into essentially spaghetti. Okay? And that process of stretching, I kid you not, is called spaghettification. Okay? And so you can ask real scientific questions about spaghettification. You can ask, how long will it take a student to, pass out due to this stretching of their body? Or how long would it take a crowbar made out of steel to break due to these forces? All fascinating questions that you can answer if you've got a PhD in physics. We are taking candidates. Yes, another question.
So my question is there a specific spot where black holes tend to appear?
Good question. Is there a specific spot where black holes tend to appear? Well, the answer to that question depends on what size of a black hole you're asking about. So it turns out that heavier things in galaxies fall to the center of that galaxy. So if your black hole is really, 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 really big, it's very likely to appear or be found at the center of the galaxy. But smaller black holes, those are lighter, they're smaller, so they don't have to fall to the center of the galaxy. And in fact, they can be produced when stars that are massive enough just explode. And when they explode, then whatever's left behind, this core of hot plasma or iron, cannot support itself against gravitation, and it collapses to a black hole. And in doing so, it gets kicked. It gets a little push due to the supernova. And so now you have a black hole that is maybe, let's say, 10 times the mass of our sun, which is a ball roughly the size of Urbana-Champaign that is now traveling at 500 miles an hour, shooting out through the galaxy. And those can be anywhere. And because they don't emit light, we cannot see them. So those are a little bit freaky. But fortunately, they're small enough that the likelihood of them hitting us is like 0. But yeah. So some of them in the center, some of them everywhere. So.
If you're in a black hole, do you see anything?
If you're inside of a black hole, would you see anything?
Or like, would you feel anything? Or
good question. So if you're inside of a black hole, what would you see? That's a very complicated question because light gets all distorted inside of a black hole. So how do we see things? We see things because light gets to our eyes. Our eyes are great sensors. When light hits our eyes, it sends an electrical signal out into our nerves that then communicate to our brain and tells us, ooh, Sammy, you saw something. That's how you see something. So in order for you to be able to see something, light has to hit your eyes. But if you are looking toward the center of the black hole, nothing that is emitted like closer to the center can reach your eyes because it's all like folding back. So if you look into the black hole, you see nothing, you see black. But if you turn around and you see toward the outside, now you can see a pretty awesome movie of the universe coming to you, and it would all look very distorted because gravity turns to stretch all of the light signals that come to you. Okay, so it would be a pretty funny video, and some people have made pretty bad movies about what you would see when you fall into a black hole. Some are better than others. And yes, there are Hollywood movies too about what you can see. There was another question over there.
So I know there's a limit to how much mass a star can have before it becomes a black hole.
Yes.
And neutron stars are rather close to that limit in comparison to other stars. So have we detected a neutron star colliding with a neutron star and then becoming a black hole because of that collision?
Great question. Have we detected 2 neutron stars colliding with each other and then becoming a black hole? So that's incredibly difficult to observe because neutron stars are really far away from us and they're very tiny. So unless they're actually shining this beam of funneled radio waves at us, we cannot see them. We have seen these things, these pulsars, and they are sometimes in orbit around another pulsar. And very creatively, we call that a double pulsar. Okay? Sometimes we see a pulsar going around a white dwarf. Sometimes we see a pulsar going around another star, like a regular star, and sort of cannibalizing that star. That's sometimes called a low mass X-ray binary, but it doesn't matter. Okay? But these things are so far away from each other that it would take forever for them to spiral into each other. Okay? They do spiral into each other because they're emitting gravitational waves, and gravitational waves are taking energy away from the system. And so the energy that the binary system, that the orbit had, is getting depleted. It's like it's running out of gas, and because it's running out of gas, it's sort of spiraling in. But gravitational waves are very weak, so they're very inefficient at taking energy away. So it's like your gas tank is punctured, but like a needle, right? And it's like dropping like a drop every like day. And so it would take many, many days for you to lose all the gas and for the binary to collapse, right? And so those we have never seen. We have never seen 2 pulsars collide with each other and like observe this electromagnetically with telescopes. What we have seen, however, is the very last stages of 2 neutron stars colliding with each other in the form of gravitational waves. So we haven't really seen them, we have heard them. So in 2017, in May, July, sometime in 2017, Okay? 1708, so August, thank you. I was in Montana. I was very happy in Montana. I was doing my thing. We had this institute with this other professor, Neil Cornish, from Australia, and we were all very happy. And it's like, oh, look at our cool institute. Let's invite all these like famous professors and to, like bring them here. Look at the pretty mountains, and like talk physics and show them our institute. And two things happened. One was that some fires got started by accident, I guess, or by weather, who knows. And then everything got real smoky real fast. So it wasn't so fun for the visitors. And the second thing that happened is that the day the meeting started, there was a discovery by LIGO. 2 neutron stars for the first time had been recorded colliding with each other. So as you can imagine, and this was very hush-hush, because if you were not in the collaboration, you weren't supposed to know, but everyone knew. And of course, you know, we are like there organizing this conference, trying to talk about like physics and science and all of the exciting things we're going to do in the future whenever we detect 2 neutron stars colliding. And they had just detected them, but they couldn't tell us. Meanwhile, like half the conference is on their computers typing violently. The other half is trying to figure out what they're typing about and where is it. And it was all very exciting. So yes, and then since then, other events have been observed. That one was particularly glorious because it was like really close by. It was 40 megaparsecs away from us instead of 400. And not only that, they observed this thing collide with gravitational waves, and then they saw light from the spot where the collision occurred. Gamma rays, right? Like the stuff that makes the Hulk be Hulk, you know? And it was very brief. It was like 1.7 seconds after we detected the gravitational wave. A telescope in orbit, by operated by NASA, owned by NASA, called Fermi telescope, detected this gamma radiation. And then after that happened, every single telescope on Earth went vook, trying to observe that spot. And they observed light in every single frequency coming from that event. And so the most likely outcome is that those 2 neutron stars collided with each other. They spewed a bunch of material, generated this short gamma ray burst, and then the remnant eventually collapsed to form a black hole. We did not detect the gravitational waves during the formation of that black hole because even though the event was closer than ever before, it was still not close enough, or alternatively, our instruments were not sensitive enough at the time. Because something else that happened, you know, if you all ever like build an amplifier, you don't crank it up to the maximum volume the first time you turn it on, right? Like you just like turn it on and you hope it doesn't explode, and then you're like turning up like really, really slowly. So they did different observing runs at different sensitivities, slowly cranking up the power of the laser and so on and so forth. The 2017 observation was at one of the earliest observing runs at relatively low laser power and other technologies. So if this happened again today, it would be cooler, but you know, unfortunately, we cannot make neutron stars collide. Yes.
Did the smoke and the fire have anything to do with you guys not noticing?
No. No, the smoke from the fire was like very annoying and very sad, and eventually dissipated. But it was part of the conference. It made everything very smoky. Yes. Did you have a question like a million years ago? Or did you ask? A million years ago. Okay. I'm good.
I don't think you were alive a million years ago.
I was not alive a million years ago. I'm old, but not that old. So you mentioned the black holes that are traveling at high speed throughout the universe. Are there people who are trying to detect them as they travel around in our vicinity, or are they just kind of assuming they won't?
Well, so we can do theoretical calculations to figure out if you have 2 black holes that collide with each other, then what happens to its remnant? Or if you have a star that goes kaboom, goes kaboom in a supernova, explodes, and then the remnant forms a black hole, then what is the recoil velocity imparted on that black hole by the supernova? these are theoretical calculations. You can do numerical simulations about this. It's incredibly hard to actually observe a black hole that's moving because it's not emitting light. It's a black hole and it's moving. So it's not like we can track these black holes. We will only be able to see them for a short time when they go through like a very large concentration of matter and maybe accrete some matter and make something shine. But the universe is huge, and we don't really know where to point our telescopes at to be able to capture that effect, which would also happen in a very short time window. So to the best of my knowledge, there haven't been any detected sort of orphan black holes floating around. And for sure, like these black holes, when they form and they're moving at some speed, they're still within the galaxy where they formed. So it's not like they can escape the galaxy, because the galaxy also has a gravitational pull, and it keeps things inside it. So you would have to be traveling at a tremendous velocity to be able to escape, say, the Milky Way. And when these black holes get these kick velocities, most of it's very, very, very extremely rare for them to acquire a velocity like that. It would have to be two black holes colliding with each other, and it would have to be under very, very strange circumstances. So now we haven't detected them, but they're not likely to be floating, migrating between galaxy and galaxy. Yes.
I'm just wondering about Einstein coming up with this theory. Was it only mathematics, or were there instruments that he, other observations that he was basing his theories on? I mean, it seems incredible that 100 years after, people are proving his theory. So how? Math only, or were there instruments at that time that helped?
That's a great question, and the history behind Einstein it's fascinating, and many people have written wonderful books about it. Isaacson's comes to mind if you want a very comprehensive history of the whole thing. So
I just want you to tell me right now.
So I could talk about this for a very, very long time, but the short story is the following. When Einstein was working in 1905, after he had his big 3 or 4 papers, which eventually would earn him the Nobel Prize, he was still sort of unhappy because a theory of light, the theory of electricity and magnetism, electromagnetism, which had been sort of perfected by this Scottish guy, physicist with a giant beard called Maxwell, was completely and utterly incompatible with Newtonian mechanics, with Newton's theory of gravity, Newtonian gravitation. And that couldn't be. Moreover, there was that incompatibility. Moreover, there was an issue with Newtonian gravity that sort of disturbed him, and he called this sometimes a spooky action at a distance, meaning gravity sort of acted instantaneously. And he didn't believe that things could act instantaneously. Like things had to take some time to get from me to you for you to know that I actually sent you a signal. And that was incorporated in Maxwell's theory, but it wasn't incorporated in Newton's. Moreover, there were experimental anomalies at the time that nobody could quite figure out. The most blatant one, well, the only one I would say, was the orbit of Mercury. So you see Mercury, it's in an ellipse. All planets are in an ellipse, even Earth. Earth's ellipticity is actually tiny, so it's almost a circle. But Mercury is not. It's not negligible. It's about 0.2 or something. And when this thing goes around, it actually precesses. It creates these pedal shapes. And you can calculate from classical mechanics, from Newtonian gravitation, what the rate of the advance of that ellipse is. And it's very complicated. You have the Sun, and you have the Mercury, and then you have all these other planets that are perturbing the orbit. And on top of that, the Sun is not like a ball; it's actually more like a squished ball. And the squishiness is called the Quadruple Moment, and you have to incorporate that as well. And you put in, you dot all the I's, you cross all the H's or T's, and then you find that no, the prediction from Newtonian gravitation doesn't match the prediction the observation at all. It's off by about 40 arc seconds per century, so some number, okay? And that was unsatisfactory. So there were observations, one in particular made by this guy called Leverrier, who was a French astronomer, that was incompatible with Newtonian mechanics. And then there were theoretical issues that he was unhappy with. So people didn't quite pay attention to theoretical issues all that much, but the astronomical ones was a big deal. So one way to try to figure out what was going on was to say, well, maybe there's another planet that we have not seen that is closer to the sun than Mercury. And because it's so close to the sun, we can see it. So maybe we should point our telescopes to real close to the sun to try to see this planet. And they call this planet Vulcan, the same Vulcan as the Star Trek Vulcan. Right. So I don't know if you ever pointed a telescope at the sun. I have, by accident. Not a good idea. Things catch on fire. So they have to wait for an eclipse to be able to make this observation. It's an incredibly difficult observation, and people did this for a while and could not see any planet. So it was an unexplained anomaly and a real problem to Newtonian gravity. So it was this combination of things. Question over there.
Thank you for coming here and making this presentation. I really appreciate it. A scientist working as a producer in a project.
Crazy,
Holy moly, what is that? What is it that you did do when you were putting this together? What was your role as a producer? And what was it like working on an interdisciplinary project? And how did you grow as a person owing to this project?
Well, that's a great set of questions. So we arrived in Montana when did we arrive in Montana? In 2011. Thank you. In 2011, after looking up where Montana was in the map. And it was a job, and so jobs are great, and they don't come often, so we took it. After visiting, we liked it, we went there. And I always wanted to work on something that brought a little bit of the science that we did to the general public in a way that was entertaining and sort of capturing. So I thought, well, combining it with art would be cool. And when I started, it was very close to the century anniversary of general relativity, in 2015. And people were planning all sorts of activities associated with that centenary. So I thought, well, instead of just setting up some public talks and going around and doing that, which I didn't think I was necessarily the best at, given other people I know who are fantastic, like Neil deGrasse Tyson and so on. I was like, well, let's try to do something different. And so we created a science festival, a whole-blown science festival. It grew from a small thing we wanted to do that I thought wouldn't it be cool to make a movie, to something that was now we're doing an art installation and we have educational material and we have a movie, and then now we are producing a composition that goes with the movie, because it was a silent movie with an orchestra in a pit, and we wanted to involve the audience as well, so we gave them instruments. It was the whole thing, right? And it lasted a week, and it was really cool, and it was very, very rewarding. I felt great. It was awesome. It let me do something that was not mathematics for a little while every week, which I appreciated. And it also involved bringing in a lot of different people together to work on things that they were perhaps not used to working on. And obviously, I'm not a painter. I am not a filmmaker. I am not a composer. And so on and so forth. So I had to go and recruit these people, convince them. So we did all of this. And I always felt after doing it and resting for about a year, I was what's the next thing we're going to do? And I always thought, wouldn't it be cool to do a planetarium show in collaboration with a subset of this team? Since we had a planetarium, Montana State University has a giant planetarium it's associated with a planetarium in the Museum of the Rocks. It was perfect. And so, of course, I don't know anything about how to make a planetarium. And then very soon thereafter, I found out that nobody at the university knew how to make a planetarium show. It's very, very hard. But I was successful at, raising money to put this thing together. I had the vision of what I thought we could make the show about. And I got to convince some really, really smart and really, really energetic people to, play with me at this game of making a planetarium show. So Theo Lipford, who you saw, director of this show, and he went out and researched. He's a professor. He's the director of the Masters in Fine Arts program at Montana. He researched how to make a planetarium show and talked to experts, and then he bought the cameras and essentially he figured it out, him and his team of filmmakers and students and so on. So much so that he then developed a class at the university on how to make a planetarium show. Now it turned out I was also friends with a music professor that's into music technology, and so him and his students then created a soundtrack to this show, and they figured a way to incorporate the sounds of gravitational waves that I then sonified so that they could incorporate it into the music part of it. But we also needed a script, and I am a physicist, not a script writer. So I thought I was a script writer, so I wrote something, and then I passed it on to the director, and he's like, "What is this?" So then we partnered with people that are better at script writing, like a filmmaker, Dennis Egg, and some educators, like Irene Grimberg and so on, and together we just put this script together. And then, of course, we premiered it, and it went great. So what did I do? A lot. But by no means, this is a fruit of effort and love, I guess. And it took 2 years, and it cost about $100,000, and it's free now for people. So we give it to Planetaria to show around the United States. And so it's shown in Seattle, in Texas, in West Virginia. We're hopefully soon doing some version of this at the Adler in Chicago, and so on and so forth.
Has it changed the way you do physics?
Has it changed the way I do physics? A little bit. So thanks to all this work in trying to combine physics with art, I have become more, in my research, more diagrammatic in some sense. I think more in pictures than I did before. I mean, I still think in math a lot, but sometimes pictures help communicate ideas that can then help drive the mathematics. And so we make analogies and things like that, and it has definitely helped with that. Yes?
So why Illinois?
Why Illinois? That's a very complicated question. So it was 2019, and the world was awesome, and nobody was wearing masks. And the University of Illinois approached me and offered this opportunity to build a center here, the Center for Advanced Studies of the Universe, and they wanted me to help cement it and grow it and so on. They provided all of these resources to do that. It's an awesome university that's much larger than Montana State University, and even though I love Montana State University and my colleagues there were amazing and very hard to move, there were also really good potential new friends here with whom I could work and that I could learn from, that worked in different areas that I had not gotten to collaborate in before. That coupled to the fact that we have family that's sort of near this area in Chicago and previously, well, still in Alabama and previously in Atlanta. We think that it's easier to get to here than it is to get to Montana. And so we combined those two things and we said, great, let's go, let's move. And we moved, and then they gave us the keys to our house, and then they said, okay, now you stay here for 2 years, and they left. And it's not been so awesome, but now things are back, a little bit back, so it's getting better again. Okay, so one last question.
correct me if I don't understand, but if the gravitational waves were huge, to where we would feel them, we would feel like the world underneath us is wiggling as they pass by us?
Good question. So I have devoted quite a bit of time to think about what would happen if gravitational waves were larger, artificially larger. Like, how close would a collision of two black holes have to be for us to be able to feel its effects? And I mean, I am not a biologist or a doctor, so don't quote me here, but I think one of the first ways we would feel their effects would be through sound. Because the way we hear is through these amazing sensors that we have in our eardrum. So essentially an air pressure wave comes to our earlobes, and it hits our eardrums. This like shoots us an electrical signal that then travels to our brain and says, oh, you've heard something. That's my very naive understanding of how we hear. If you have a gravitational wave that's going through, these eardrums can actually move much more freely than the rest of our head. Mm-hmm. And because of this change in resistance, we would be able to hear the deformation or the gravitational wave of how it's impacting our eardrums, and we would be able to hear a gravitational wave if it were of the right frequency. So what is of the right frequency? Well, we would have to hear, there would have to be two black holes with the mass of our sun in spiraling and colliding where the moon is.
Okay.
And then we would be able to hear them, according to what I understand of our sensitivity to sound.
They're ripples through space-time. What is happening to time?
Time is also changing and dilating. So we don't really typically talk too much about time because it makes people's heads hurt. But time and space are one and the same in the theory of general relativity. So space can contract, time can dilate. So as a gravitational wave goes through, what we typically say is you have these two lasers that are in these arms, and the wave forces these lasers to do this dance. At one time, I convinced a friend of mine, who then became the president of the American Physical Society, to explain this to a group of children. So he called this the gravitational wave dance. And so the dance is that, say a wave is going through me, so this arm contracts while this expands, and then half a cycle later, it goes the other way. And so it goes like this, right? And so it was really funny when he did it, not so much when I do it, but anyway. And so this motion is what's causing the interference pattern of the laser light. A completely different but equivalent way of explaining that is that the arms aren't moving, but what's changing is the time of propagation of the photon between one end mirror and the and the recombination point and the other one. So the time that the photon experiences as it travels this way is different from the time that a photon experiences when it's traveling in the other direction. Okay. And those two descriptions are equivalent. And I think with that, I thank you all for coming, and enjoy the rest of the weekend.
Thank you so much, Professor Yunes. We really appreciate your time to join us here, and we appreciate all of your questions that everybody gave this evening. I think that was a really fun time that we've all had here.